Frequency?
They always vibrate in the same way.
Yep.
Now, the most sophisticated clocks are atomic clocks, and they use atomic transitions that emit light at a very specific frequency. And that's to the point that the definition of second is now so many vibrations of a cesium atom, etc., etc.
Okay.
So the time is defined as the number of, by using the fact that an atom is always the same atom. If it is the same atom here or elsewhere,
Right.
it vibrates with the same frequency. So that is what allows you to have universal clocks that would work anywhere in the same fashion.
So that's cesium has its own natural frequency? Do we state it in that fashion?
Yes.
Okay, good, good. We just learned that. We learned about frequencies and wavelengths just a few weeks ago. Thank you. Next question, please.
That's coming almost up to date.
Yeah, you're
we'll get to what you taught yesterday.
Yes, you know what? There's so much you speak of, Professor. Cesium, an atom of cesium in your pocket versus an atom of cesium here. It's the same element, same number of protons and electrons, so it's universal. And it's the same cesium that may be on Mars or where else. Thank you. Next question, please.
Approximately how long does a unique tool such as the LHC accelerator remain the best in the world? How long do you think it would take before this kind of technology is surpassed?
Wait, you are too close to the microphone or something. It vibrates a lot. Can you ask your question
Go up
again,
front.
please?
Amanda, would you mind, please?
Approximately how long does a unique tool such as the LHC accelerator remain the best in the world? How long do you think it would take before this kind of technology is surpassed?
Oh, I hope very little. It's very difficult to make predictions, particularly about the future. And the accelerators that we have at the moment are very close to being at their maximum possibilities, because we only know how to make better ones by making them bigger, which is not very intelligent. But there are a lot of investigations on how to accelerate particles differently. And one of them is if you want to accelerate a positively charged particle, like a proton, instead of that you accelerate a bunch of electrons which have negative charge and capture the proton in the middle. So you accelerate this whole thing, and then what you're interested in is in the proton which is being accelerated. So you discard the electrons and you have a proton very well accelerated by the wave, so to speak, that is moving like that. It's like surfing on the sea.
Yes. So this is an analogy. Good. We're good, Amanda? Yes? Good with that? Okay, Professor. So a couple more minutes of your time, if we may?
Yes.
Okay, thank you. Next question.
Do you
You want to come on up, Caitlin, please. Another star student of mine.
Do you focus more on experimental results or the theoretical explanations?
I'm so sorry, the connection is so bad that I didn't hear it. I mean, I heard it, but all scrambled.
Speak a little louder, please.
Do you focus more on experimental results or the theoretical explanations to those results?
Oh, I'm so sorry. Sorry, you'll have to be very patient with me. My microphone is probably not excellent.
Do you focus more on experimental results or the theoretical explanations?
Oh, no, I'm a theorist. And although I focus on experiments because that's where the reality is, I don't go and do them. So I make my own mistakes, but they have nothing to do with connecting cables.
Thank you, Professor. Thank you, Caitlin.
Another very good question that I happen to remember and I want to answer, and somehow we got it lost.
Okay.
I think someone asked whether it was dangerous to go to higher energies.
They did ask the question, yes.
Yes. Now the answer is we know that that is not the case. And we know that because there are cosmic accelerators, the explosions of supernovae, that make particles of much, much higher energy than the ones we can make in the laboratory. And those particles impinge on the surface of the atmosphere. They are called cosmic rays, and they interact with the they interact with nitrogen and oxygen in the atmosphere at energies which are much bigger than the ones we can produce. And we know that in such collisions, there has never been the creation of a dangerous object. If that was possible, then there would be things such as what is called neutron stars that are very dense balls of nucleons, the size of the 10 kilometer size or so, of the mass of the sun, very, very, on which are also impinged. And they would have, if you create something dangerous like a new kind of black hole, they would have eaten the neutron stars in our galaxy. So we would see no neutron stars. So we know from observation that the collisions at even more energy than the ones we can produce are completely harmless.
So safety is not an issue. That was not a concern of yours as a result.
Well, it's occasionally a concern of people who like to be concerned.
Yeah. It makes it sensational, but it's unsupported, and it kind of distracts us from the matter at hand, I guess. Good. Thank you,
Yes.
Professor.
So, since it's not a bad question, it's also interesting to answer it very specifically and in great detail and with great power.
All right, thank you, sir. Maybe one or two more questions, and then we'll thank the professor. Next.
My question is
Come on. Okay.
Do you have to stand up?
Yeah, would you mind?
All right, yeah.
Allison, speak nice and loudly.
All right, my question is, what is antimatter useful for, and can it be stored without destroying its container?
Antimatter.
Antimatter is useful in various ways that have been demonstrated. For instance, there is what is called positron electron tomography, which is a way to quote-unquote X-ray people very, very finely. And what is done in this medical technique is you inject a person or an object or an animal a nucleus that decays into positrons. Positrons are the antimatter particle corresponding to the electrons of which you are made. Now, if you have a positron in your body or any other body, it will find an electron and they annihilate, matter-antimatter annihilate, and they produce two gamma rays, two particles of very high energy light. So you have from the body of the person being studied from specific points where this element has concentrated, you have two particles of light that allow you to take a photograph, so to speak, very precise photograph of your guts, of your interior. So antimatter is already useful in medicine. And in the future, it will also be useful, this time in the form of antiprotons, which are the particles of antimatter corresponding to protons. They will be useful in burning very efficiently very small and localized tumors. For instance, tumors in your eye. Those, in the future, maybe not the far future, could be very, very precisely burned by having a beam of antiprotons impinge in your eye and stop precisely where the tumor is. Now, I hope that doesn't happen to any one of you or your families, but to those who have such very dangerous, very small tumors, antimatter may also be useful in the form of antiprotons.